Let's take a look at a few examples. So we want to describe the span of a single two-dimensional vector, vector 1, -2. So by definition, this is going to be the set of all vectors that can be expressed as a linear combination of this one. Now there's only one vector here, so we would only multiply this one vector by some scalar. Which means our span is every scalar multiple of this one vector. Okay, we can see it a little clearer maybe if we draw it out. So our vector is the vector 1, -2. So 1, -2. There's the vector. And now the span is all linear combinations of that one vector, which in this case means all scalar multiples of that one vector. So if I multiply it by a positive scalar, I could go in this direction, all along this line. And if I multiply by a negative scalar, I could go in this direction, all along this line. And so this span is going to give me a line in two-dimensional space. Okay, let's take a look at another one. Now let's describe the span of two vectors in two dimensions. Okay, so by definition, this will be the set of all possible linear combinations of these two vectors. So any vector that can be written as some scalar times the first vector plus some scalar times the second vector. For any two scalars, a1 and a2. Okay? So what would this look like? So again, it might be helpful to sketch out our two vectors. Okay, so we have vector 2, 3. Make that a little thicker. So vector 2, 3. And vector -1, 2. So -1, 2, right there. And with a little thought, you might realize that we can reach any vector in the plane by looking at a linear combination of these two vectors. Okay, so I think about it like these are the only two directions you can travel, but you can travel as far as you want in either direction. Where can you get? Can we get to vector W, for example? So I just drew a random vector. Can we get there? Okay. Well, maybe we go backwards here, little ways, trying to eyeball this. A little more than that, I think. Maybe about to there. Yeah, that's about right. Okay, and then we could go in the direction of 2, 3, and we just scale it. Okay, Now, I just picked W randomly. We could get there. We can actually get anywhere in this plane by using only these two directions, by only moving these two directions and then changing how far we go in those directions and whether we go forwards or backwards. Okay, that's the scalar part. The scalar determines how far we go, and if we multiply it by a negative, we could also go backwards. Okay, so these two vectors span the whole plane. The span, or let's put it this way, the vectors span the entire plane of R2. The entire two-dimensional space. Okay? All right, let's look at one more. Again, we want to describe a span of two-dimensional vectors. Now we have two vectors again, so you might think right away that that means we're going to span the entire plane. But let's check. Okay, so it's the set of all linear combinations of these two vectors. And so our first vector is negative 2, 3. Negative 2, 3 right there. And our second vector is 4, negative 6. And after a little thought, you're going to realize that we can't span the whole of the plane in R2, right? This vector can only move along this line, right? It can move forward or backward, but can only move along that line. 4, negative 6 can only move along the same line, forward or backward. So this span is going to be restricted to just one line. So the vectors span a line in two-dimensional space. Okay, well, what's the deal? Why is it that with the last one, our two vectors span the entire plane, but for this one, I have two vectors again, but they only span the line. So in this case, our vectors are in some way redundant, okay? So if we have some vector v that can be described as a linear combination of our two vectors, okay, so then it could be described as some constant times our first vector plus some constant times our second vector. But we notice something interesting. Because our first vector and our second vector lie on the same line, they're pointing the same direction, or I guess opposite directions in this case, they are scalar multiples of each other. Specifically, 4, negative 6 is negative 2 times negative 2, 3. So anything that the portion of the linear combination that's being described by the vector 4, negative 6 can also be described by the vector negative 2, 3. Okay, I can swap out vector 4, negative 6 with negative 2 times negative 2, 3. And so if I factor out the vector negative 2, 3, I'd get the scalar a1 minus 2a2 times vector negative 2, 3. Okay, and that's going to be for any vector that is in the span of these two vectors. And so this vector is kind of redundant. We don't need it because we can describe any vector in the span with just this one vector. And that's going to be the case whenever we have one vector that can be described by a linear combination of the other vectors. So in this case, 4, negative 6, just negative 2 times negative 2, 3. And so it's not really adding anything new to our description of our span. Okay, and so we get the same set as if we just had one vector, a line in two-dimensional space.